Hello?
Yes. Okay, so let's start. This morning, so we'll have two reviews as usual, but the first one is live. So here is like Tomasz Kacprzak from like the Swiss Data Science Center in Zurich. And he gladly accepted to talk about like the relation between machine learning and how to best use them for galaxy surveys. So you have the floor, and I will make you a small hint.
Thank you very much. Great. So, good morning. We're going to do a review on how we are already capitalizing on artificial intelligence, machine learning, SBI for large-scale structure cosmology. So, we heard a lot of very interesting, promising, wonderful ideas for future analysis in this meeting already. But since it's a review talk, I will focus on the past. And I will tell you about what kind of machine learning analysis already have been applied to data, the focus that papers that already been published on real data experiments and delivered constraints, and historically how we got there. Now I'm going to focus mostly on AI or machine learning based approaches. Of course, there is a whole field of simulation-based inference, or generally inference using simulations in different ways as theory prediction. I will focus mostly on AI, even though there is a lot of very interesting analysis using human design statistics that use our own intuition about what features to use from our data. Reviewing that would probably take another talk. So I will focus on the machine learning, but from time to time I will also bring in some of the human designed analysis, which are, I think, very important, and I think basically doing both AI and human-designed analysis is extremely valuable and will help us to better understand our data and our cosmology. So I will also talk about simulations, and I will definitely focus on those which already has been used as theory prediction for cosmology measurements, and those critically that are public. Finally, I will give you some ideas what I think could be the next challenges in building simulation-based inference from, well, the data science perspective or methodology perspective. All right, so let's get started. So I will broadly talk about three things: how to reach the information flow of the data, then also about how to break the degeneracies between cosmology and other astrophysical effects or systematics. Some call it systematics, some call it physics, depends where you are. And also I'll talk about accelerating simulations, but in this section I'll also broadly talk about simulations in general. All right, so let's start with the first one. Okay, so why I think that reaching the information flow of our data is very important is, first of all, we have one universe, so we have one realization. So we cannot repeat the experiment like folks at CERN for a long time and get more data. We also spend quite a lot of effort and money on wonderful satellites, telescopes, data pipelines, running operations for these experiments, building cameras. And with that, this is fantastic, but there is a notion of diminishing returns with this. So our constraints are shrinking as a square root of the area that we measured. So if we run our survey for twice as long, we'll only shrink our error bars by roughly 40%. So it's worth to keep that in mind. So if we are able to invest fraction of the effort or money into building simulated theory prediction and methods that can capitalize on that and shrink the error bars by 40% just doing that, I think it's a worthwhile enterprise. And to illustrate that, I have this picture that was made by DALI by Florina Ciorba, who's at the University of Basel. That kind of highlights the point I want to make, is that we have our wonderful telescope, but we also have a big computer. And the big computer can be a kind of an equal partner in this whole endeavor. And we can use our remarkable capacity to simulate the universe. Well, still big work in progress, but it's actually really good already, to bring those two together and maximize the information we get. And bringing the computer as an equal partner is also very cost effective. All right, so just to give a little bit of a background, we already repeatedly here talked about capitalizing on non-Gaussian information in the density field, but we also talked about interpretability and how do we know what features are extracted, how we know what things are learning. So to address that, I always like to think about it as, okay, we are very familiar with power spectra. We've seen them thousands of times. We know the values by heart of their amplitude and how they change with different cosmology parameters, but we rarely look at maps. And I made this map compilation from our simulation set that basically flies through redshifts from high redshift to low redshift at different cosmologies. So here with we're probably most likely living somewhere here. But if we bump up, if we have a lot of matter, so matter density is high, then we would map look something like this. And then we have high dark energy, we would have something like this. So you can clearly see by eye already, right, how the feature is changing. And then similarly, high S8, low S8. The differences are subtle, but we can see them, right, in these maps. Even if we just look at W0 of -4 and the rest, the other parameters being very similar, there is, well, we can see the difference, although it's very subtle, but I can immediately notice that the voids are a bit more pronounced, right? Of course, there's way more to talk about that, but this is just an example how we can build our intuition about connecting simulations and cosmology and what features there are. Okay, and there's also motivating picture that these two fields have the same power spectra, but one clearly has more features than the other. And there was, here we can clearly see that, right? It's really obvious, but different probes will look at this density field in different ways. So we'll have gravitational lensing, for example, our flagship SBI analysis. It probes this density field, but it integrates along the line of sight with a very broad kernel. So it washes out a lot of these really complicated structures. On the other hand, we have galaxy, so also lensing is very noisy. So the shape noise is a really major source of uncertainty here. On the other hand, we have galaxy clustering, which has a much narrower projection kernel for, let's say, photometric surveys, but modeling of that field, so galaxy bias and HODs and all this is very complicated. So the signal is really high, modeling is very hard. And then we have 3D redshift surveys, which give us 3D information, which is even more powerful. But then, yeah, selection functions also can be complicated there, together with all the biasing problems we would have. So let's talk about weak lensing, because this has been the probe that has been delivering already AI constraints. This is just another intuition picture. We have two mass maps simulated, one from low sigma 8, low omega m universe, the other one high, and there's a little moon. So if you look at the sky, you can kind of connect this intuitively. You can see by eye the features are very different, but this is also a very high resolution map. So if you wanted to find out, okay, how much can we actually gain from analyzing that with some method that we hope can get to the bottom of the information floor, can get everything there is in this data. So how much is there? And this depends on two quantities. First is the noise level of the survey. So we have a stage 3 survey with, say, 10 galaxies per square arc minute. We have some level of noise. We have Euclid with hopefully 30, or LSS, Rubin. So quality of observations will depend on our experiment. So if you add noise, we'll get a noisy map like this. And this is on the side of the telescope. And on the other side, we have quality of simulations, which is on the side of the supercomputer, so how well we can actually simulate this. And this is the smoothing scale. And I want you to remember this smoothing scale as a key number here. This compares to basically the scale cut in various analyses. But I noticed that in multiple analyses, especially when they're being compared, people not necessarily track the smoothing scale that is being used in SBI consistently and don't compare necessarily apples to apples. So in my talk, I will always try to bring in this number, the smoothing scale, either in sigma or as a size of the pixel on the map. So you can keep track of which analysis used which smoothing scale. And why is this important? Well, I'll come back to that, but first, I will share with you how we started doing this with and quantified how much more information is there to gain from lensing. And this is in the context of these experiments. How much can we gain? Before that, I will just bring in a little history. So this is actually the first neural net that I think was published, actually by my master's student, Jorit. And there's an interesting story to this. We only could do classification, so we just classified cosmologies. We've had the same power spectra, 5 different models, compared to other higher order statistics, and found out the networks are working well. We never managed to actually get the paper published. It took us 3 rounds of review, and ultimately, by the 3rd round, we already had the next paper out, so we just gave up. But Jorit, who was running this, had this particular problem that was at the time the big thing, was how to make it work for very noisy lensing data, right? So we needed to figure out how to have a schedule of ramping out the noise slowly, otherwise it just wouldn't work. Nowadays, this is really not a problem, but in 2016, it was. And so Jorit actually then went on to work in industry, and he grounded one of the most successful AI startups in Switzerland now, which has to do with how to build vision systems for self-driving cars and other industry cameras that deal with very difficult weather conditions when there's a lot of rain and snow and everything is very noisy. So we count that as a good contribution. Since then, so that was very noisy, but classification. Here, the first result was from the Columbia group. That was on noise-free, but regression, so actually getting constraints. And here, the pixel size was very small, so very high resolution maps. And for noise-free data, obviously CNN beats power spectra plus peaks. So that was already a very good hint that maybe it's worth to invest in that. And critically, the comparison with Gaussian random fields was very reassuring because there's no more information for Gaussian random fields that power spectrum can extract compared to CNN. So those two should give the same results. That's the information flare, and they were giving that. So it was a very reassuring result that the network is not imagining anything here. And in this work, we quantified, made a forecast for how much is there to gain for the smoothing scales that we think we can reliably analyze without going too much into the baryon territory. I will come back to baryons also later. And we did this forecast saying how much is there to gain for stage 3, stage 4 surveys, and how this advantage over power spectra behaves if we change smoothing and noise, right? So what we found that for a smoothing scale of 2.3 arc minutes, we are getting around 40% better constraints, which than the power spectrum, which basically means that, we would have to take twice the amount of data to get to that with power spectra, which is a huge amount of improvement compared to the effort put into it. The simulations for this are, less than, order of a couple of 100,000 francs these days, or euros or dollars. Whereas running the survey for a couple of years, it's a huge enterprise. And other things that we found is that if we increase the smoothing scale, the advantage basically disappears. So we converge towards the results from 2-point. But if we go from, if you compare the noise levels, actually the advantage is similar. So it's still worth to do this on noisy data. And we already started to see that at this scales we are slightly getting affected by baryon feedback, although not too much. This is a bit looking more into that because this is a very important part about the smoothing scale and the scale cut. What we see is that the advantage of networks just really blows up if we go to more smoothing scales. So if you see the results where people, like when you see the, for example, numbers, like we improve by 100%, by 200%, always check at which pixel scale or which smoothing scale this is. Because if we go to the left, we can get 1000% easily. All right, and then we are going to baryon territory. Okay, and the first measurements, also made by Yanis Furi on Kids for 50 data, tomographic and basic ResNets with follow-up likelihood analysis with 3 parameters. So I also mentioned which always try to keep track of which parameters we're able to constrain. And here we put a lot of effort in checking whether the choices we made in simulations were actually impacting the results on what level. So we did things like, okay, if we switch from PKD graph to gadget, how much would the results change? If we switch from ray tracing to Born, how much the results would change? If we had high resolution with more particles, how would the results respond? And here, so we tried to do a very, at the time, I think, quite extensive, but now we would have, of course, more ideas how to test a list of unblinding criteria. We found that we were still sensitive to baryons. We couldn't actually put the baryon parameters on the grid at the time, but we noticed that if we use that with that smoothing scale, we would be affected to more or less that level. But nevertheless, knowing that, we unblinded our results. So these tests, what I call modified mock observation tests. So the idea is that we have, let's say, the initial conditions that are the same for the standard simulation that is used to train the system. And we made an alternative simulations with the same initial conditions that has something different, like say higher resolution or baryons or things like that. And we compared the response. So the stochastic noise should be more or less the same, but the delta in the cosmology would give us some indication about how what's our sensitivity to this, what's the sensitivity of the system to this. So this is one of the ways we can test. The other way is convergence tests. I mean, a little bit related, where we, let's say, increase the number of particles by a factor of 2, make the box bigger by a factor of 2. Just see what happens if we spend more computing on it. Would we get a different result? This is what I call convergence, to converge to a specific output, regardless of your effort, not lensing convergence in this sense. Okay, so it was blinded analysis, and this was the Kids for 50 result. Which gave, as we expected, around 40% improvement, especially in this banana direction, a little bit higher than other kids' analysis, maybe a little bit due to the baryons. But we also found a different value for intrinsic alignment. I will come back to intrinsic alignment later also. And they're broadly consistent with some differences. So, yeah, that was the first result. Since then, what we've done in terms of measurements with kids was to scale it to Kids 1000, where we put the data on the sphere. We use a new simulation suite. I will come back to that. And we added W parameters, and we put baryonification on the map level. Also come back to that. In the spirit of moving carefully, we also didn't try to reach for the stars and go to smallest possible smoothing scale. We wanted just to reproduce the Kids 1000 results with machine learning and do a lot of tests to see if everything agrees. Not necessarily improved a lot on the results, just to touch base on the same data, very similar parameter set, baryons, and relatively large smoothing scales. And here's our conversion test for various configurations of simulations where we tested our results about. And this is the output. So we got very consistent results with Kids 1000 in WCDM space. Our W measurement is limited by this prior. Here we couldn't simulate anything because of the ghost in the simulation. There's no time to talk about that in this talk. But generally speaking, also not very constraining, but we didn't find any surprises. And analysis was blinded. Okay, and since then, this analysis of HSC UER1 data was performed by the Columbia group again. And this is also relatively fresh, I think this year. And also very impressive analysis when they managed to marginalize over baryons, 4 parameters. Systematics, and what, on the other hand, didn't manage to marginalize over other parameters. They used a pretty conservative but quite good smoothing scale of 4 arc minutes. And for the first time, which I want to highlight, it's amazing, proposed a way to marginalize out PSF contribution possible PSF contribution to the data by forward modeling the PSF leakage. So this is really great. It's one of these small details in the paper that make for one of the most amazing things in the paper. So improvement was also, 5 to 24%, and really good improvement on omega m, so basically shrink the banana. It's really great. And also improved IA measurements, but I think their model had fixed redshift. And I didn't find the word blinding in the paper. Maybe I didn't. Maybe it's written in a different way, but I didn't find it. I'm sure Zoltan will correct me later today if that's the case. All right, so I think this is where we are with the results, with the state of results in lensing for AI for lensing. But at this point, I want to just highlight the competition between human and machine. Our ability to constrain gets with a reasonable smoothing scales, we are at 40, 30%, which is great. But we probably can do similarly well with human-based statistic. And this is just an example from DES year 3 from Dominic Zurher, who was also at ETH, on the full DES year 3 peak count analysis with all the cosmology parameters when we aim to constrain sigma 8 omega m intrinsic alignment, marginalize about a range of other things, and build this peak function emulator. So this is the number of peaks that has, when you subtract the number of noise peaks and you overplot the S8 signal. What we found here, which I think is quite interesting, is that the CLs and peaks had a little bit different dependence on intrinsic alignment on the map level. Here we used NLA with evolution with evolving with redshift. And that was a pretty interesting hint. Okay, so maybe we can actually gain something, not necessarily on the cosmology, but on being more robust to our systematics in astrophysics or, systematics generally. So this is the degeneracy breaking starting to appear here. All right. And yeah, again, improvement was really good. So 40% for combined CL and peak analysis, and pretty stringent blinding. All right. So this was on the side of weak lensing, but galaxy clustering is coming in recently into play, and then has been 2 papers published within 1 day. I'm not sure if those coordinated or not. Maybe some of the authors are here. It would be really good to talk to you. But I find this really amazing. So first, I think, well, if we want to go in order, I think that was first. So galaxy clustering CNNs using the Bose mass sample, and basically using a large simulation set from Quixote. I'll come back to the simulations later also. Constraining 5 cosmology parameters. The smoothing scales were actually quite conservative, which is really great to see that even with that you can get a big gain. So 11 megaparsecs, that's equivalent of, I think, something like smoothing scale of 5, 6 arc minutes, depending on redshift. And then, pretty impressive training with 3-dimensional CNNs and 2.65 improvement to compared to correlations only. And also, I didn't find the word blinding in the paper, but it's still under review, so probably worth to just keep in mind. But marginalized over 9 HOD parameters, which is really impressive, and probably was quite a big challenge when it comes to operations and data wrangling, using this SimBig forward modeling framework. So what they find, okay, great improvement. One thing that immediately starts to pop up, that the value for H0 is on the low side, which does it put a new point in the H0 tension table? Yeah, I think this is where we're starting to face reality. How much do we interpret this result compared to others, which may be already more mature? All right, then, so that was machine learning. Here we have wavelet scattering transform, different team, different simulation set. Whether wavelet scattering transform is machine learning or not, it's kind of blurry line, but They also use the Abacus Summit simulations and same data, 4 cosmology parameters, a little bit smaller smoothing scale, 6 HOD parameters, and yeah, wavelet scattering transform plus correlation gives improvement of 2.5 to 6, which is amazing. Also H0, pretty constraining, so yeah. Also, I didn't find the word blinding, but maybe please correct me if there was blinding in analysis. So this is, I find this very exciting. So I remember saying that lensing is very noisy and has a very broad integration kernel. 3D clustering, no problem like that, if we can model galaxy distribution in connection to dark matter correctly, and if we model spectroscopic selection functions. So I think there's, I think it'd be really great to see more of that analysis in the context of SBI. All right, how are we doing for time? Good. All right, so this is where I think we are with results from LSS and machine learning, SBI. If I missed something, I'm really sorry. Please let me know. I will tell you about these 2 things that I'm quite excited about also. So there was a forecast recently to see if we can improve constraints on neutrinos masses from LSS using SBI, and it's quite promising. I think there's probably even more one could do in that direction and to improve this. But yeah, what happens if we detect or we measure neutrino mass with SBI, and then how much do we trust the result? I think that would be really interesting. This is one of the unique things I think we can do. And there's another big cloud on the horizon that's coming to us. It's SKA. The data challenge for that will be incredible. And I think the machine learning / simulation-based approaches will be not only nice to have, but also probably indispensable. Especially that a lot of the observables from radio are, yeah, highly nonlinear and will have to be analyzed using simulation. So this is, was a prototype already a while back for 21 centimeter analysis, where a lot of these astrophysical parameters and cosmology were proposed to be constrained simultaneously with very good accuracy. So yeah, I think that's also very promising avenue to work on. All right. So let's switch gears. That's, I think, the state of the results and some promising future applications. I'm sure there's more in this room. So now I want to talk to you about something a bit more profound and ties into what Thorsten was saying a bit earlier, generally, how to use AI to break some of the degeneracies between cosmology and astrophysics or other systematics. And it comes from this problem we had in Dark Energy Survey, where we were wondering which intrinsic alignment model to use, and there are people in this room also that participated in that directly. I was just reviewing that paper. So here what we have is a situation when we have data which is not particularly well constraining when it comes to intrinsic alignment, but we have to make a choice about which model to use. And if we use the wrong model, we can get a really biased cosmology. So let's say our universe was tidal alignment, tidal torque, but we use the NLA model, we would get pretty bad bias compared to this X here. If we use other models, we could, the results can change as well. So there's a question what to do in that situation, and there have been some number of papers written on that. But generally speaking, the whole problem comes from the fact that we don't have a lot of constraining power on these parameters, and if the universe has quite a high value of tidal torque, so the A2 parameter in the intrinsic alignment, but we use a model that is as NLA, we can be biased. And okay, there are 2 approaches. One to basically marginalize, parameterize, marginalize, but still that can lead to projection effects due to our priors not being, well, having a huge influence on the data. And, but yeah, we can use a simpler model that we risk underfitting. So what I think could be useful here in SBI is that if we can shrink the constraints on these parameters by using map-level inference, we can explore a larger parameter space of models. So we can be more robust, we have more robust cosmology if we have well-constrained astrophysics. So this, I think, like probably one of the immediate benefits that I'm the most interested in checking right now. So yeah, the more constraining power, and we'll be more robust. Maybe we'll not deliver much more precise cosmology parameter measurements, but we will know that we are not highly dependent on these effects because we have a larger model to constrain. And in this deep LSS prototype analysis that got published in PhysRefX, actually, we explored these questions, and we had this combined probes of lensing and clustering, and of course intrinsic alignment comes into play here as well. Generally, for those of you who are not very familiar with IAs, we have these physical fields, weak lensing, clustering, alignments, but we only observe galaxy shapes and galaxy positions, and the shapes contain noisily weak lensing and intrinsic alignment, and we have galaxy positions which are biased with respect to the density field. So those are observables, and if we use that, we can parameterize nuisance parameters that control these astrophysical fields, such as galaxy bias, stochasticity, intrinsic alignment, amplitude, its evolution with redshift, and we can compare power spectrum analysis, and we can do the neural net analysis. And here we would put clustering and lensing in a tomographic sense as channels, right, similar to colors, and get the network to try to figure out the connections between these channels and how to extract the information from the field. And in this prototype, we found that, wow, it's really, really good. Especially for intrinsic alignment amplitude, we're getting practically degeneracy breaking effect. Other parameters also improved quite a lot, and overall impact on cosmology was great. Of course, this has to be taken with a big grain of salt. It was just a prototype. There's way, way more to do in real data analysis, but I think this merits some interesting investigation. So this is just a zoom in on intrinsic alignment. And we saw this result, and for a couple of months we were thinking, oh wow, is this a fluke? Is there some bug in the code? And we spent quite a decent amount of time looking into that and trying to interpret the result. So we looked at the saliency maps, which basically probably many of you in this room are already familiar with. So how much impact does each pixel have on the prediction for intrinsic alignment that is outputted by the network? So this is the sensitivity map as for lensing. So this is the lensing convergence. And if there's a pixel that lights up either red or blue, it means that this area in this map would have higher weight on the final result. So where did the network start to take information from? Well, these blobs, which also correspond to the blobs in the galaxy clustering map. Please ignore this guy over here. So you have these three blobs, and this is where the information is being pulled out. So the network just to try to focus on these regions, ignore anything else, effectively downweight or pay less attention to that area, pay more attention to these areas that it finds relevant. So it ties into what Thorsten was saying of how we weight the signal. Where do we put our attention? I think neural nets can potentially be really good at finding the optimal weighting of the pixels, especially in a multi-probe combination that will localize the information and try to pull it out from there. Again, with a grain of salt, but interesting. So this is where I think that can bring a lot of benefit. And when it comes to interpretability, there was also some amount of work. This was a paper by, again, the Columbia group on how to interpret the weak lensing analysis. There is a whole literature in machine learning about interpretability. So if you want to learn about that, recommend Wojciech Samek's book on this. And there are multiple ways to perform this task. So again, which pixel informs the decision, right? And if we have some input lensing map, we can have all these interpretability measures. Most of them seem to be putting some information on these blobs here, but some of them are giving something weird. So question, how to interpret the interpretability maps? No, I don't know myself, but I think it's already getting, it's very interesting and also quite reassuring that the information is not just taken from one pixel somewhere in the corner of the map. All right, so final slide on this section. just want to say about the current efforts in dark energy survey, where we doing the combined probes analysis with machine learning on relatively conservative smoothing scales, especially for clustering. And this is some of the fields that we are using. And if you want to learn more, go to poster by Arne or talk to Agnes. All right. And here I want to pose the data science challenge, which we already talked about a lot, but I just want to make sure that people understand how important and critical this is. How do we make ourselves, how we convince ourselves that the model we have is a good fit to the data, which is relatively straightforward to do if we have just a very nice curve going through the data points with remarkable precision. And then we can compute something like reduced chi-square, goodness of fit measures. There's a lot of statistics literature on that. But what do we do if we have stochastic fields? That's with more profound, more complicated. There has been interesting approaches towards that. So first of all, we can always split the data in multiple ways, by the area of the survey, from this corner, that corner, by redshifts. There's been a really interesting paper recently about doing that scale by scale in a machine learning framework. And also foundation models are coming into play, so maybe that can be part of the solution to this problem. But to my mind, I don't think there's a mainstream method established yet or a methodology established yet to do this well. So I'm very interested to talk to anybody who is investing in that. Okay, so now I have still a couple of minutes, 10 minutes probably, or maybe 15. So well, let's talk about simulations, accelerating simulations, but first I will go through simulation sets that has already been used in applying them to data and making practical measurements. So the simulation that started it all, Dietrich and Hartleb 2009, this is Jörg. It's a really wonderful person, left academia unfortunately, but this simulation set has been used massively in the early peak statistics papers, including mine, and it has 128 cosmologies. Actually now it's only 157, because they were stored on hard drives, and one of them failed, and we lost one cosmology. So it's been a really great data set to work with, and many people used it. So thanks, Jörg. And then the next one, which was a massive success, is the Cosmos-Lix. And it's been used for the DES Y1 peak counts, as well as really a lot of different forecasts. So those are very interesting simulations. They're pencil beam in 4 parameters. They have really high resolution. So, yeah, I think something went wrong with this, but it's roughly 1,500 cubed particles in a 500 megaparsec boxes. So high resolution, very good. Unfortunately, there's a lack of baryon feedback modeling, but still. Very useful data set. This is a plot of how year 1 DS was chopped up to use as 10 by 10 degree pencil beam patches. Very nice. And then latest forecast for Euclid, we also used this data set and produced a Fisher analysis for 11 different non-Gaussian statistics, which is really, really interesting, seeing the community coming together and building this and treating this higher order as a serious alternative probe, a complementary probe to the classical analysis. All right. Then the next milestone was the Quixote simulations. This is, again, everything I'm talking about here is public. With this data set, so here we had a relatively small number of cosmologies. So if you're extracting your features like peak counts, you can build an emulator and smoothly interpolate in the cosmology parameter space. That's okay. Similarly, here there was there was a lot of simulation sampled on a hypercube, and it had 7,000 cosmological models and had central simulations and derivatives, which was very useful. Relatively low resolution, so 1 gigaparsec boxes with 500 cube particles. A lot of simulations stored as snapshots at 4 different redshifts. So because we don't have smooth light cones, it's hard to use it for some probes, but for other probes it can work. So there's always this this design decision of what simulations to build targeted on what probe. I think I'll come back to that design question later. And again, amazing public simulation, Abacus Summit. This is an incredible data set, 2 petabytes of storage. So just to give you a hint, if you want to store 2 petabytes, so 4 petabytes, including backup, that's around $500,000 or francs or euros. So it's a huge investment. And this simulation is incredible. It has 139 points in the cosmology space. 97 cosmological models, 139 simulations, and stored a lot of data products, merged the trees, light cones, halo catalogs, and everything you need to put the HOD models onto this. And run on Summit, which is one of the largest supercomputers in the world. It's a really a treasure trove of information, what you can do. These are the cosmologies, and again, here we are in the mode where we have few points, but if we are building summary statistics that can be nicely interpolated across the space, then it's fine. Then it's completely everything that you need for this. And I want to go to Cosmogrid V1, which is a data set that myself, I ran together with Yanis. So I was the PI of this project at Swiss Supercomputing Center, which was a large production, largest one you can get in Switzerland. And we went in a different direction with the simulation set. We wanted to sample the space very densely and build a theory model that gives us the distribution over maps. So going towards a thing that you can sample from and get a map, a full couple of million pixels on a Hilbix grid, without deciding on summary statistics ahead of time. So naturally suited to machine learning approaches. And we built 2,500 cosmologies in this densely sampled grid, including dark energy, with this funny cutoff prior, with 2 grid levels, one broad and one narrow. Obviously, we want to spend more time training in the region of the data that we expect the constraints to be. And for each of these 2,500 cosmologies, we have 7 unique initial conditions. So we have 7 independent simulations. We store light cone shells, so Hilbix maps on 70 shells from redshift 0 to 3.5. So it's targeted stage 3, early stage 4 lensing and clustering results. And we have a lot of benchmarks. So what happens if we have a bigger box? What happens if we have more shells in a redshift resolution? And critically, for the first time, I think what we have for SBI was baryonification. It's a BCM model, baryon correction model. I will tell you about that now in a second. So it's not perfect model, but it's a start. So at least we can tell how sensitive we'll be to this to parameters of that model. So this is the difference between the baryonified and the dark matter only versus baryonified. So you can compare the color bars here. You can see that for halos, what it does, it like pushes out a little bit the mass from the center, which is what we expect the baryons to do. Yeah, already been used in a number of publications. It's all public. Yeah, one more thing about the baryon model, because since it's a review talk, I think it's good to tell more about how all of this work. And it's also an area which requires more investment and effort. So I would really encourage you to if you're interested to work on this topic, I would as well myself. So this is a baryon connection model from Schneider and Tessier, and what this does is mimics the impact of baryons on the dark matter distribution. So it goes into the simulation and uses halo model formalism to displace particles. So what we do is to first measure the NFW halos in the simulation and make the parametric profile of them. And then we modify this profile using baryon correction model parameters. So this is the standard profile, the initial profile, dark matter only. And the final profile is this, this red one. And you can modify it with different parameters depending on your baryon feedback physics. So the procedure is, yeah, we find the halos, we modify the halos, and then we find the displacement for each particle. So we move the particles around a bit, like we've seen in these other pictures. Does it work? Yeah, you can see that they're moving in and out a little bit, depending on whether you're, what you're doing. So that's how it works. Okay, this is what a lot of methods use to marginalize. Nice property of this is that it can mimic a lot of different hydro models on the power spectrum level, and it also can be constrained. So the parameters of this model can be constrained with other observations like X-rays and so. So we can use those as a prior in our analysis. But again, how well does this reproduce our baryon physics compared to hydro simulations on the map level? I don't think it's a question that anyone has answered, and I will be very interested to know. Okay. How much are we doing for time? 15 seconds? 2 minutes. Okay, so I'll go a bit faster here. So I'll skip this. The data is available for Cosmogrid. Okay, other amazing public simulations that are worth mentioning. I don't think they were applied to data, but Camel SAM and Massive Newts, also highly impactful. And yeah, just in the last 2 minutes, coming back a little bit to the baryon question, Tilman, who is here, proposed this wonderful approach that can repaint using machine learning the baryons from full hydro simulations. This was used using Bahamas at the time on another dark matter. So you can get this additional field learned on one simulation applied to another. And this one can be potentially a good solution for if we really want to push to the small scales and get this massive benefit of machine learning compared to the power spectra. We would need to figure out how to include baryons on this grid simulations or in some other way using SBI or other work approaches. And I think machine learning can play a very big role here. And it's something I'm quite excited about following up. Of course, I think in this room I don't have to mention Camel's a really huge step in understanding all this. Another work that since Tilman's initial ideas has been taken forward a little bit on from a University of Zurich group where they used a zoom-in simulations with hydro. So they managed to connect some of the large scales and the small scales and this kind of multi-scale approach. And they managed to build a repainting engine using degenerative adversarial networks to include baryon effects onto dark matter only simulations. Okay, so this leads me to this challenge, second challenge that I want to put forward maybe, how to build multi-fidelity simulations. So if we want to have a reliable SBI with a lot of different effects that will give us a robust cosmology and that we can trust, and we try to put all our knowledge of how to simulate the universe and build a nice theory prediction on simulation level, on pixel level. I think it would be very difficult to do it in just one simulation code. We probably need to do multi-fidelity approaches on a kind of simulation ladder when we use hydro in some way combined with maybe machine learning and going towards full, painting it on dark matter and so on. So there's been some work on the multi-fidelity approaches actually on the power spectrum for now, but I think this is a really cool idea where you just basically, what you do is you have cheap simulations with the blue, expensive simulations with the red, and you try to learn from those combinations and predict for some test points that were the crosses. And yeah, I think that's possibly one way to go about this. And yeah, so how to build this system that does this consistently and reliably with percent level precision. Okay, sounds hard, data science challenge. And possible answer can be also foundation models. All right, so that's bringing me towards the end. I think just to summarize everything, I think where we are with SBI and AI, we have already present gains going into areas of like 30, 50% for lensing with the scales we can simulate reliably. Clustering is becoming very promising, so first results are already out. And the upcoming gains that we kind of want to expect in the near future would be this expanding this astrophysical systematic space into galaxy biasing and intrinsic alignment so that we make sure our results are robust to those modeling choices. And so this upcoming and the future, generally going beyond astrophysical systematics, going beyond the kind of WCDM standard models, and testing some more exotic models that we can simulate. So dark energy, dark matter, gravity theories. There's a lot of people building simulations for those exciting models. And with AI, we have a better ability to test them. Right? So I think that's potentially the future, but also very exciting. OK, thank you.
Thank you very much for the motivational talk. We can take some questions now. Henry and Nabila.
Yeah, thanks for the very nice talk and the summary. Supposing I already know my cosmology, how much work has been done, for instance, if I wanted to know from a galaxy catalog or what are the properties of the underlying dark matter halos without going through the usual business of fitting a model directly from a set of simulations?
Sorry, could you...
The question is, if you've got your galaxy catalog and you assume a cosmology, can you tell me what kind of dark matter halos are in my galaxy catalog?
In terms of...
The properties of the dark matter halos and all that kind of stuff. People have worked on that a bit.
I don't know if... I mean, one could build a dedicated system to answer that question directly. But I think unless we explicitly focus on that, it will be probably quite hard. So yeah, it would have to be a network that kind of gives you the output of that kind of question. Yeah, but possible, I guess.
Thanks for the presentation. I have a curiosity question about the comparison between the output of the emulators when you try to explore the different cosmological models. So you had a small number of cosmological models, and then you have basically produced much larger ones. Is there a comparison that was made on the fidelity of the emulated results versus the results which are effectively using actual simulations in this parameter domain?
So you refer to the clustering, to the 3D clustering results. OK, I don't know myself. These results are quite fresh. I looked through the papers, and I think my impression would be that I would probably, if I was reviewing them out, also ask the same question. I think for lensing we did really a lot of different checks, including looking at how these emulators perform, quantifying their precisions, and there were really way too long appendices on this, which I didn't see necessarily in these papers, but well, one step at a time, I guess.
Yeah. The calibration requirements for both current surveys like KITS and DES, but also for Euclid and LST, have all been designed for two-point statistics, so to make sure that the two-point statistics are accurate, probably most importantly for automatic redshift calibration. So you propose to use statistics that are significantly more powerful in terms of constraining power, and they have different sensitivity. So how can you make sure those are robust?
Yeah, that's an excellent question. I think we can go probably for the same process as deriving requirements for two-point, and we can find where do we stop, how conservative we want to be with our analysis. So for example, for redshifts, we can marginalize the uncertainty on our n of z's, and I definitely recommend to marginalize not only the shift, but also the shape of the distribution, if possible. So that's possible with SBI, that we can plug in. If these are well characterized by the redshift team, I think those uncertainties can be propagated relatively reliably. But for example, with the analysis we are now challenged by in dark energy survey, we really want to go to much more conservative scales. Right? This is the scale question again here. So yeah, we also test various scenarios. As I mentioned earlier, we create mock observations that have some effects on the map level that we did not include in the simulation grid, and we check whether the output is robust to that or not. And if it is, then we have a problem. We cannot unblind, right? So we have to design the analysis to be invariant to that or marginalize it, or yeah. It's a challenging process. It's a lot of work to do it reliably. But compared to building another telescope or observing for twice as long, I think it's a time well spent still.
Yeah, thanks for the really nice talk. I was very interested in what you presented on the sensitivity tests and the, well, like goodness of fit test. So obviously, for a two-point function, we're not only doing goodness of fit, we'll have Gaussian of null test, compatibilities between different cuts of the data. I'm a bit frightened by the level at which the thinking about those different tests for SBI is right now. It really looks like the dream, or rather the nightmare, presented by David Weinberg yesterday. Yeah. So where are we going here, and how much effort is poured into this thing? Because, and it goes, well, in the same line as what Henry was asking, like, okay, you get a set of simulations or emulated simulations that looks like the data. Have you tried to extract other information to actually check that those are close enough, or measure how far they are and say whether it matters or not for your cosmology and for your results? I mean, this is really important. Otherwise, nobody will believe in these results.
Yeah, absolutely. Yeah, no, I think the challenge of testing this is large. Is maybe more difficult than for 2 points. Significantly more effort will have to go to this.
Actually, the challenge of testing the validity of 2 points is much larger than just doing the measurement to start with.
Yes, exactly.
So it should be the same here, even worse.
Absolutely, yes, I completely agree. The huge responsibility on tests, and I cannot stress this enough. I think what we can do, be a little like friendly adversarial game. We'll have the skeptics who will come up with all the unblinding tests that we have to pass as the enthusiasts. And we can go back and forth, and this way we will just keep improving the quality of our measurements. I think, yeah, like switching to the thinking of how to actually test this is critical here. And that should be probably more effort than actually designing the analysis.
Yeah, but it's more than just blinding and doing a few tests. It's really about trying to really build a statistical understanding of your data and test for the, well, what we're doing on 2 points is testing for a single summary statistics. Here we have a lot of summary statistics that we know of that we can test, and we can build, again, with simulation. You can try to approximate the expected distribution for the summary statistic. You can test the compatibility of all of the different things you can measure from your simulation and from the data. I mean, there's lots of things that you can do here. I'm very surprised that this has not been thought of yet.
Yeah, I think, generally speaking, there's a lot of interesting analysis prototypes, and for a prototype, one doesn't really have to do that, right? For measurements, yes, there has been a number of measurements, and we've done our best for lensing at the time, and the bar is becoming higher and higher now with dark energy survey, where we go through a committee review and the collaboration review and all that. So, yeah, I think you're completely right. We are, by now, I mean, Arne can probably tell better than myself, we basically just use the most vanilla method there is on SBI and just put all our effort into testing and validating and coming up with new methodologies to test this. I think that's important. It's not only about methods, it's about methodologies in how to do the science. So yeah, I'm very interested in those. I historically also work on testing and calibrating shears and all of that, so yeah.
Thanks for the talk. It was great to see all of the simulations available for these simulation-based inference analyses. So I guess my question is, typically when we perform these kind of analyses and lensing, we often need simulations that are tailored to our given survey for things like the redshift distributions of the galaxies, or perhaps the footprint of the surveys embedded into the simulations. So although these simulations are available, do you know, in general, can they be used for any survey, or are they really just tailored towards certain ones?
Right. Yeah, I think the simulators, design some data products from the simulations, right, and make them public, hopefully. And then there's another layer of how to make forward models for the experiment, right? So we've built forward models for DES. People who did clustering, I'm sure they did a good job in modeling the selection functions for spectroscopic surveys to make the raw fields, physical fields, galaxy fields, dark matter, and to match what the survey would see on the level we can invert it, right? So whether it's a mass map or a shear map, galaxy catalog, yeah. So this step is typically taken care of by people working on the survey, but it's usually not that hard. Maybe with the exception of spectroscopic selection, but I'm not an expert on this. So those processes, the forward process, usually one can do relatively straightforwardly.
Okay, thank you. So I think that we expanded all the immediate questions and comments. So let's thanks again, Tomasz.